Hello and welcome back to my CATIA V5 tutorial. In the previous video I made, we learned how to design spur gears, we learned how to design internal ring gears, so naturally the next step is to put them all together and design a planetary gearbox. A planetary gearbox is a type of gear arrangement that consists of one or more planet gears rotating around the central sun gear. It is a speed variation device known for its compact design, high torque density and efficiency. They can provide various gear ratios and are commonly used in applications requiring high power and precision, such as automotive transmissions and robotics. The arrangement allows for a high degree of load distribution and can achieve significant reductions in speed while increasing torque. A planetary gearbox has four components: the sun gear, located centrally, the planet gears, typically evenly spaced around the sun gear and are driven by the sun gear, the ring gear, an outer gear that encircles the planetary system. This has internal teeth and meshes with the planet gears. And finally, the carrier, which is a piece connecting the planet gears together and spins concentrically to the whole system. From now on, to make things clearer while using the formulas, we will call the sun gear gear A, the planet gear gear B, and the ring gear gear C, and we'll refer to the carrier as D. It turns out, in order for a planetary gearbox to work, it needs to respect a few conditions. First, and most important, is the number of teeth on the ring gear needs to be equal to the number of teeth on the sun gear plus 2 times the number of teeth on one planet gear. So it's ZC equals ZA plus 2ZB. This will satisfy the necessary center distances for the gears to match. Secondly, the number of teeth on the sun gear plus the number of teeth on the ring gear divided by the number of planet gears needs to be an integer. This will assure the gears will be evenly spaced around the system. And finally, not as important but still important for it to work, is you need to satisfy this condition to allow the gears to mesh without interference. I say it's not as important because this usually checks out, and if this doesn't check out, you designed the mechanism horribly wrong anyway. So, after we respect these conditions, we need to pick what type of gearbox we want to make. There are three types depending on the element we assumed as fixed. First, we have the planetary type, where the internal gear C is fixed, and the input is the sun gear A, and the output is the carrier. It's this type of arrangement, and it looks like this. So you see, the gear C is fixed, and everything else moves. We have the solar type, where the sun gear A is fixed, the input is the internal gear C, and the output is the carrier, which is this one. Move it the other way around so you can see how it looks like. And finally we have the star type, where the carrier is fixed, the sun gear A is the input, and the output is the ring gear C. In this configuration, the ratio is simply ZC divided by ZA, and the planet gears are just idlers. They don't factor in the calculations at all. It looks like this. Now you can see here I have my three mechanisms in one assembly. This has been actually really hard to do, and I highly recommend you do not do this. You need to have one mechanism per assembly. So, how do we do this in CATIA? Well, first we start by designing the gears, and then we throw them together in a product. If you have not designed the gears yet, I will not do them today. You can check out my videos where I designed the spur gears and the ring gears. I will link them in the description and somewhere on the screen. But generally speaking, what you need to do is to make sure you have gear with the ability to input these type of parameters. You need to make sure the module is the same between all the gears, the pressure angle is the same, and then you can edit the number of teeth using this parameter here. So you can start however you want. For me, I just start by choosing the number of teeth for the big ring gear. So I chose 130 teeth for this, and then I chose 50 teeth for the sun gear. Using the first formula, we calculate then the number of teeth for the planet gears, and this adds up to 40. Inside one of the gears, we have the calculations for the center distances, which is A. We only need to do it for one gear, and this comes up to 135. We have the 50 and the 40 z times the module divided by 2. So then we just position the gears and we start making the mechanism. So we start by creating a new mechanism. Insert new mechanism. First thing first, we need to set a fixed part. We choose one type of planetary gearbox and we choose the planetary type where we have this one, the ring gear fix. We start by creating a rigid joint like that. And we have our input then, which is going to be a revolute joint. And it's going to be this gear. And it's going to be related to the fixed element, which is something imaginary hidden in our case. We have the YZ plane, angle driven. Mechanism can be simulated now, but we don't care about that. And we will have our output is going to be the carrier. Again, you need to link this to the fixed part in order to create the gear. This one, this one. Okay, so if you want to create a gear joint, both the elements you want to connect have to be defined in relation to a common element. So now here you see this is a revolute joint between sun gear and the fixed part, and this is a revolute joint between carrier and the fixed part. If you were to define it to something else here and not the fixed part, it will not work. A gear joint will not be able to be created between the two. And we need to calculate the ratio. We said before the ratio is going to be the number of teeth ZC, which is 130 divided by 50 ZA plus 1. So this is 3.6. Good. We needed to have this angle driven, and now the mechanism can be already simulated, but we still need to define the planetary gears. We do this. How do we do that? Well, we need to link them to the sun gear. I think it's the easiest way to do it. So to do that, we need to create again this revolute joint, but this time we will link the sun gear to the carrier. And why is that? Because we need to link the planet gears to the carrier, and then this one needs to be linked to the carrier in order to create the gear joint. We will not click angle driven here because then it's going to cause an issue. Although this is like a double revolute joint, we already have one joint defining this. It's fine because this is not driven, and this one is already is part of another gear joint, and you can see you don't get the error. Okay, now we create this joint. And we create the gear joint between them. So this is going to be minus 125 because it's actually 50 divided by 40, it's 125. Mechanism can be simulated. Now before doing the rest, we need to check to see if this is actually okay or not. We put the increment here 1. And then we see. So this joint looks okay. However, this one looks very, very not okay. So what could be the issue? The issue is because the order in which you select them matters in CATIA. So our ratio that we calculated here, 3.6, it's actually a reverse ratio. So you need to start the calculator. and you need to do this 1 divided by 3.6 and copy this here, and you see that actually this is the correct ratio. So now it works fine. I think you need to always be careful to leave this in 0 when you close it, otherwise it can cause issues with your synchronization issues with your mechanism. Now you do the same links for these two planet gears. Right, so there you go. This is how you design a planetary mechanism in CATIA V5. It's not as straightforward as you would think. These gear joints are a little bit difficult to do and really counterintuitive. That's just the way it is. If you found another method of doing this, I'm happy to take a look. Just let me know in the comments. And this has been it for today. Thank you very much. Please don't forget to leave a like and subscribe to my channel. And I'll see you next time.